Okay, now we are going to solve another problem for drawing of a shear force diagram and a bending moment diagram for a simply supported beam which is carrying a uniformly distributed load. Okay, so this is going to be our problem. So what is the problem is that SFD and BMD for simply supported l- simply supported beam with UDL. Okay, so uniformly distributed load. So UDL is nothing but a uniformly distributed load. So now let us consider a beam like this, simply supported beam. One is pin support, another is a roller support. Okay, there will be the two reaction at pin support, horizontal reaction, vertical reaction, and at roller support there will be the only one reaction. It is a statically determinate structure which can be analyzed with the three basic equation of static equilibrium. Okay, so this is a simply supported beam. Now there is a uniformly distributed load UDL. Okay, so UDL is like this, which is constant throughout the length. So it is W per unit length. W per unit length. Okay, what it means that for every unit length of this beam there is a load of W is there. Okay, so this is a problem. Now we are going to calculate the shear force diagram. We have to draw shear force diagram and bending moment diagram, and for that we should find out what are the support reaction of these beams. Okay, for that, to calculate, very first step will be to calculate support reaction. Calculate support reaction. We know the very basic equation of a static equilibrium that were covered in engineering mechanics. Okay, so there are three equations also. Static equilibrium equation, there are three equations, that is summation of all the forces in x direction is 0, summation of all the forces in y direction is equal to 0, and summation of a moment about z axis, it is also 0. So these are the three basic equation, okay, that can be used and a statically determinate structure can be analyzed. Okay, analysis is nothing but the calculation of knowing the shear forces and bending moments along the length of a beam is nothing but the analysis. So now we are going to apply equation summation of Fy is equal to 0 to know the or to determine the what we can say is reactions of this beam. This is the point, suppose this is A and this is point B. So there is a reaction RA and this is reaction at point B. So for summation of Fy, the forces which are going in upward direction will be considered positive and the forces which are going in a downward direction will be considered as negative, like this. So now reaction at a point A, it is in upward direction, so that is RA will be positive, plus this is the load, that is nothing but a UDL, uniformly distributed load, that is the load which is distributed uniformly. This is, so W is acting per unit length. Okay, so what does it mean? That if you are having 5 meter length, then on every meter there will be load equal to W for every meter. So length is 5 meters, so that's why the total weight that is acting on a beam will be nothing but a 5 multiplied by W, that is nothing but the 5W. So like that, on this beam W is acting per unit length and which is acting on all over the length of a beam. So that's why, and it is acting in a downward direction, so that's why total load will be W multiplied by L, and it is in acting in a downward direction, so that's why it will be considered to be negative, so that is minus W into L. Okay, again there is a RB which is acting in upward direction, so it will be considered as a positive, that is nothing but the RB. This is equal to 0. So RA plus RB is equal to WL. This is a very basic equation we got for this calculation of this support reaction. Now another equation is that is summation of all the forces, all the moments is equal to 0. Now taking bending moment at a point 8, summation of moment at A will be 0, because why? Because it is stable. So that's why now we calculate the bending moment at a point A. It is a pin support again, so that's why definitely there is a bending moment is going to be 0. So when I take the moment at this point, then there are the two forces which I see that can be rotated about this point, that is one is RB and another is this UDL. Okay, so one of the important point is that this UDL will act at the center of a span on which it is acting, so it is acting on all over the length of this beam. Okay, so its a point of application will be at the center. Okay, so how much total load is acting is nothing but the W multiplied by L, that is WL, and that will act at the center of a beam, that is nothing but L by 2. Okay, so and it will rotate the beam, it is in clockwise direction. So I'll calculate the moment. Clockwise moment is considered positive, anti-clockwise moment is considered as negative. So W per unit length, so total load will be W multiplied by this length, that is nothing but WL, and this UDL always act at the center of a span over which it is distributed, so it will act at a distance of L by 2, so WL into L by 2, that will be the clockwise bending moment. So it is acting in a clockwise direction. I am taking moment at A, so it is in clockwise direction, so that's why it will be again positive. Now if you consider this RB which is acting in anti-clockwise direction like this. Okay, so it is in anti-clockwise direction, so that's why it will be considered as negative. Okay, so RB is we don't know how much is RB, so RB is RB into L is equal to 0. RB into L, it is anti-clockwise, RB multiplied by perpendicular distance, that is nothing but the L, so that's why RB into L. Now we got W L square by 2 minus is equal to RB into L, this L and this L get cancelled, and WL by 2 will be the reaction at point B. Okay, so it will be the reaction, RB will be WL by 2, so this is 2. Now putting this value of RB in equation 1, RA plus RB is equal to WL, that was our equation. RB is equal to WL by 2 plus RA, this will be equal to WL. So RA is equal to WL minus WL by 2. Therefore, how it can be calculated? WL multiplied by 2 to WL minus WL by 2. So that will be equal to WL by 2. So RA and RB are same, that is RA is equal to WL by 2. So this beam is basically symmetric, so that's why reaction at A and reaction at B are same. RA is WL by 2 and RB is also equal to WL by 2. Okay, so we got RA WL by 2, RB WL by Now calculation of shear force diagram calculation. Okay, we are going to calculate shear forces along the length of a beam. Again, what are the sign convention? That also matters. Okay, let us draw the sign convention. Suppose this is the section. To the left it is upward, and to the right, if it is in downward direction, then it will be considered as a positive, and if this is like this, it will be considered as a negatives. Okay, so these are the sign convention basically used. Now shear force at a left, shear force at left side of this point A. So this is point A. Okay, and this is the left side. Okay, so I have taken the section at this. If we consider the left side of this section, there are no loads, so definitely there is not going to be any shear force. That shear force at A left will be 0. Okay, now shear force at A right, nothing but this point A, and this is section at the right. Okay, at right side of a section I have right side of A I have taken the section shear force at A right. Actually we consider this two sections only when we consider to the section to the left. We do not consider this RA. When we consider a section to right of this A, then we consider this reaction at point A. That is the only the difference. Which can be made by this taking the section at left and right. Okay, so shear force at A right, when we consider, we have to consider this reaction WL by 2. Okay, so this is the only reaction which is acting at this R at this point. So shear force at AR is nothing but WL by 2. Now shear force at B left. Okay, so shear force, this is the B point and this is the left side of a point B. So this is the section, this is the section I have taken, which is to left of the B, and I am going to calculate shear forces at this point. Shear force at B left, when it is to the left, when it is in upward direction, it will be considered positive. Okay, when left side of the section, when it is in upward direction, it will be considered positive, and when there is a downward force in the downward direction to the left side of the section, then it will be considered as negative. Okay, so now shear force at B left, so RA, which is acting in upward direction, so as it is acting in upward direction, it will be positive, that is nothing but WL by 2 positive. Okay, but now this is W per unit length, which is acting in downward direction. Okay, so that's why left side of the section acting in a downward direction, so that's why it will be considered negative. So it will be minus WL. Okay, so how much it is? WL by 2 minus 2 WL, that is nothing but this minus WL by 2. Now shear force at B right. So this is the B point, and I am just taking the section to the right like this, adjacent to this point B. Okay, when I am taking the section to the left, I am not considering this reaction. When I am taking the section to the right, I am considering the reaction. That is the only difference that can be made by considering the section. Okay, so there is not any another logic in that. So shear force at B right. So we know what is the shear force at the B left, that is nothing but a minus WL by 2. Now we have to consider this only reaction. We have to consider this reaction, that will be nothing but plus WL by 2. So minus WL by 2 and plus WL by 2, that will be equal to 0. Okay, so this is how the shear force diagram calculation can be made. So just draw the diagram here, and again then we will plot it below the beam. So this is the reference line, 0, this is 0. Shear force at A left is 0, so this is the point. Shear force at A right, that is WL by 2, again it is positive, WL by 2. Now shear force at B left is minus WL by 2, means this is minus WL by 2, and shear force at B right is equal to 0, isn't it? So join this line like this, joining these 2 points. This is nothing but a shear force diagram. Okay, so this is the variation of the shear force along the length of a beam. As there is a UDL, means there is a constant load, the variation is inclined and linear. Okay, so let us draw this shear force diagram below the beam like this. This is WL by 2, and this is also WL by 2, and this is x raised to 1, means it is a linear variation. Okay, like this the shear force diagram will be. Now calculation of bending moment diagram. So for calculation of a bending moment diagram, so this was a beam like this. Okay, this is the RA free body diagram I am going to draw. This is WL by 2, this is also WL by 2. There is a UDL acting on a beam, that will be nothing but W per unit length. This is L. Actually, while calculating this bending moment diagram, we also need this shear force diagram. You know, this is the SFD. Okay, shear force diagram. This is WL by 2. This is also WL by 2. Okay, whenever there is a change in sign of shear force diagram, there will be the, what we can say, there will be the bending moment. There is a maximum bending moment when there is a change in a shear force diagram, sign of a shear force diagram. So this is the positive, and this is here, it is a negative. So at this point there will be the maximum bending moment. Okay, but we will go by our method. So calculation of bending moment diagram, calculation of bending moment diagram, how to go with this calculation. So this is point A, this is point B, and consider this point as a C. Okay, bending moment at A left, this is A point. I have taken the section like this. Okay, at the left side there is a no any load, isn't it? And again important, that is the sign convention for bending moment. Like this, if it is, then it will be positive, and if it is like this, it will be negative. So left there is a no any load, at the left side there is a no any load, so that's why there will be no bending moment at all, it will be 0 at A left. Now bending moment at A right, means I am considering the section at this point. By this I only make the difference that once I consider the reaction and once I do not consider the reaction. So this is WL by 2 is nothing but a reaction, WL by 2, but it is passing through that point only, A only. Okay, so moment is nothing but a force multiplied by perpendicular distance. There is a no any distance between A and this reaction, this point, so that's why it will be multiplied by 0. So bending moment at A right will be again 0. Now bending moment at B left, if you are going to calculate, then how much it will be? This is the point, B left, that is again in upward direction. It is acting this reactions, that is WL by 2, left side of the section, so it will be again positive, and this is the left side, so it is in a clockwise direction, so that's why it is positive, WL by 2 multiplied by L. Okay, so multiplied by L, because from this point to this point the distance is L, WL by 2 multiplied by L. Now this load, that is uniformly distributed load, which is acting in a downward direction and causing the rotation of a structure, having moment in anti-clockwise direction at this section. So when it is in anti-clockwise direction, it is considered as negative, so that's why negative. W per unit length, so total load will be W multiplied by L. Okay, and that will act at the center of this span, that is nothing but L by 2. Okay, so this is WL square by 2 minus WL square by 2, so this will be also 0. Bending moment at B left will be also 0. Now bending moment at B right. Okay, means I am considering the section like this. Okay, right side of this B, and I am taking the moment of all this at this point. So again it will be reaction at A, which is in causing the moment in a clockwise direction. So it is WL by 2 multiplied by total length minus this UDL again WL, and acting at a point of a distance of L by 2. So that's why it is L by 2. And this reaction, that is RBWL by 2, it is only passing through this point, so it won't create any moment, so that's why it won't be considered. Or if you consider, then you have to just write that it is 0, WL by 2 multiplied by 0, because there is a no distance, so that's why if you consider this WL square by 2 minus WL square by 2, okay, then okay, again then it will be also 0, like this. So as I already told you that whenever there is a change in sign of shear force diagram, okay, then there is this point is considered as point of a maximum bending moment. So let us consider bending moment at C left, which is the point C left, WL by 2 WL by 2, so it is actually the midpoint of this beam. Okay, so how we can calculate? That is nothing but a reaction which is in upward direction, that is WL by 2 causing rotation in a clockwise direction, so that's why it will be positive WL by 2 and multiplied by L by 2. Okay, minus, we are considering taking the bending moment at this point. Okay, like this. Again this is the load which is acting on it, and it will be in what we can say at W per unit length. Okay, it is acting on half of the beam length of a beam, so that's why it will be W multiplied by L by 2, that will be nothing but a total load, and it will act at a midpoint of this span, so that will be again WL by 4. Okay, so WL square by 4 minus WL square by 4 4 into 2 8. Okay, WL square by 8. So when we calculate this, then you will get the bending moment WL square minus 2WL square by 8. Okay, and you will get the value is equal to WL square by 8, and it will be again positive. Okay, so how will be the bending moment variation? It will be